Hello everybody, how's everybody doing? CRS here. This video comprises of all those questions that are most important for your board exam from the chapter Electric Potential and Capacitance. So make sure you keep yourself hooked up to these videos so that you can ace your board exams numericals very well. Let's look at the first question. The first question says charges of 2 microcoulomb, 4 microcoulomb and 6 microcoulomb are placed at three corners ABC respectively of a square ABCD. Let us imagine this. We have a square here, that is a square, and now let's make it a little big and name it ABCD. So let me name this A, B, C and D. There is a 2 microcoulomb charge according to the question, a 2 microcoulomb charge placed at A, 4 microcoulomb charge placed at B and 6 microcoulomb charge placed at C. Find what charge must be placed at the fourth corner so that the total potential at the center of the square is 0. So let's assume that here is where the center of the square is, and the potential at that point is supposed to be 0. That is what you are looking at. Then obviously positive charges at any point will produce a positive potential and negative charges would produce negative potentials. But these are all positive charges. So there must be some negative charge that is producing a potential at the center equal to the sum of all the potentials produced at that point due to charges kept at A, B and C. Now, that's all the logic is. Let's say that the distance from the corners of the square to the center is all x, right? So all these corners and this distance, let's say, my dear friends, is x. That's where the point is. This distance is x, this distance is x, this is x and this is x. Of course, the side of the square has been given to you as x, then this can be x by root 2. That would be x by root 2. Since the question says you can take it to be any distance, but because the question says that the side of the square is x meter, this is x meter, each one of these would be x by root 2. All right, this x by root 2, my dear friends, can be written in the question as, if you like, r, but that's okay, we shall continue to write it as x by root 2. Let's say the charge kept at D is supposed to be Q, and we will find what that Q is. The total potential at the center O is due to the charge kept at A plus charge kept at B plus charge kept at D plus charge kept at D. So the potential at O is due to charges A, B, C and D. Now that's what I mean by writing that. Anyway, you have potential at the center O to become equal to 0 because that's what the question asks you to do. What should be the charge at the fourth corner so as for the potential at the center of the square to become 0? When that is the situation, just equate it to 0, and you see there is a 1 by 4 pi epsilon naught in all of these. This is 1 by epsilon naught, 1 by 4 pi epsilon naught QA divided by distance AO, maybe I'll call that O, and let's write that down. 1 by 4 pi epsilon naught has been pulled out as a common factor. I shall write it as QA divided by AO plus QB divided by BO plus QC divided by CO plus QD divided by DO. Now that's your question. It's answer, right? You can send 1 by 4 pi epsilon naught to the other side, it will become 0. So we have QA divided by, you can pull out AO as a common factor. AO is equal to BO and that's equal to CO, that's equal to DO as well. So because all of them are equal, you can call them AO, AO, AO and AO. So we have 1 by AO multiplied by QA plus QB plus QC plus QD, right? and that should become equal to 0. Now AO is x by root 2, but then you send it to the other side, it will anyway become 0. It doesn't really matter. Let us start substituting now. QA, my dear friends, is 2 microcoulomb. That's a 2 microcoulomb. Plus QB is 4 microcoulomb. QC is 6 microcoulomb. And QD has to be figured out. Do you see? 6 plus 4 would be 10. 10 plus 2 is 12. Send it to the other side. The charge that is to be kept at corner D is minus 12 microcoulomb. And that's the answer to your question. As simple as that. Now, this charge minus 12 microcoulomb will produce exactly the same potential but negative potential when compared to all of these three combined. So that the total potential at the center of the square would become equal to 0. Let's look at the next question. Let's look at the next question. ABCD is a square of side 2 meter. Charges of plus 5 nanocoulomb, plus 10 nanocoulomb and minus 5 nanocoulomb are placed at corners A, B and C respectively. Let us visualize this scenario. We have a square and let's say we have the square, a square of side 2 meter. So there you go. So this is a square of side 2 meter. Let me name these corners A, B and C. The question says that a 5 nanocoulomb has been placed on at corner A, a plus 10 nanocoulomb has been placed at corner B, a minus 5 nanocoulomb has been placed at corner C, and there is corner D, right? Let's find out what is supposed to be done. What is the work done in transferring a charge of 5 microcoulomb? So there is a 5 microcoulomb charge that's going to be kept at corner D to the point of intersection of diagonals. So if you just see where the diagonals would intersect, so here is the first diagonal and there is the second diagonal. The diagonals intersect at this point and you have to bring a minus 5 5 microcoulomb charge from this place, which is corner D, to the center of the square, which is O. So we need to find the work done in moving this charge from D to O. How would you go about solving this question? Very simple. Watch. There is going to be a potential at point D due to all the three charges kept at A, B and C. We call that potential the initial potential VI. Initial potential VI can be written as potential at D due to charge kept at A plus potential due to at D due to charge kept at B plus potential at D due to charge kept at C. Now this is 1 by 4 pi epsilon naught. There is a 1 by 4 pi epsilon naught in each of these terms. So I'd like to pull that out as a common factor. Inside you will have charge placed at A divided by AD plus charge placed at B divided by BD plus charge kept at C divided by CD. This is the potential at the initial point. Well, let's find what this is going to be. The potential at the initial point now is going to be 9 into 10 to the power of 9 because that's what is 1 by 4 pi epsilon naught. Now you have a 5 nanocoulomb, 5 into 10 to the power of minus 9 divided by this distance. The question says that the side of the square is 2 meter. So AD is also going to be 2 plus there is a 10 nanocoulomb charge. A nano is 10 power minus 9 divided by BD, which is root 2 times the side because it's a diagonal. Diagonal is root 2 times longer. I would like to write 2 root 2, right? Because 2 is the side, root 2 times longer is 2 into root 2 minus I have minus 5 nanocoulomb. That's 5 into 10 to the power of minus 9 divided by 2 because the distance to point D from the minus 5 microcoulomb charge also is 2. So when that is the situation, you have initial potential Vi being equal to, you see this gets cancelled, and all you have is 10 power plus 9, 10 power minus 9 also getting cancelled. When that is a situation, you can now write 9 into 10 as 90 divided by 2 root 2. 90 divided by 2 root 2. Now 2 ones are maybe, and that's 45. So you have 45 divided by root 2. 45 by root 2 volt. This, my dear friends, is the potential at the initial point. Similarly, you can write the potential at the final point. I'm going to skip a couple of steps because we now know how to do it. Potential at the final point, which is potential at O, my dear friends, is going to be equal to, potential at O due to charge placed at A plus potential due to at O due to charge placed at B, potential at O due to charge placed at C. So 1 by 4 pi epsilon naught will certainly come out as a common factor. So I have 1 by 4 pi epsilon naught multiplied by Q A divided by AO plus QB divided by BO plus QC divided by CO. That's all you have. Now, simplify this and you have 9 into 10 to the power of 9 multiplied by 10 to the power of minus 9. It's been pulled out as a common factor. This is plus 5 and that's minus 5, just like in this case. QA and QC will get cancelled. Multiplied by QB, QB is 10. Nano has been written already. Divided by, my dear friends, this is half the diagonal, right? If you just look at what is AO, BO and CO, anyway QA by AO, all of these distances are the same. The diagonal is root 2 times longer. I just said that 2 root 2 meter it is from here to here. The distance AO is half the diagonal. Half the diagonal, my dear friend, just 2 root 2 divided by 2, it gives you just root 2. That's all it is. So you can simply write it divided by root 2, because anyway QA and QC got cancelled with their denominators. All you have is root 2. The reason being, this is 5 divided by root 2 and this is minus 5 divided by root 2. So that's all you have. Now going further, all you have now is 90 divided by root 2 volt. That is the final potential. The next step to finding the answer is finding the potential difference. The potential difference, my dear friends, is final potential minus the initial potential, and that turns out to be 90 divided by root 2 minus 45 divided by root 2 is also 45 divided by root 2 volt. This is your potential difference. When that is the case, you can now calculate the total work done. Work done is simply the product of charge that is being moved. Charge that is being moved is a 5 microcoulomb charge, and the potential difference delta V. The charge that is being moved is here, that's a 5 microcoulomb, and then you have delta V. You multiply 45 by root 2 with 5 into 10 to the power of minus 6, and I'm sure you will get 159.123 into 10 to the power of minus 6 joule, and that is your final answer. That's how you do work done problems. You can have any problem in this manner and you should be able to crack it with ease. Hope this helps. So 3 steps. 1, writing the initial potential, writing the final potential, and calculating the potential difference. Work done is charge that is being moved into potential difference. Remember, while you are calculating the potentials here, you must not take the potential due to charge that is going to be moved. So you need to only take potentials due to stationary charges. With that knowledge equipped, we will go to the next question. Let's look at the next question. The next question reads, 2 charges 3 into 10 to the power of minus 8 coulomb and minus 2 into 10 to the power of minus 8 coulomb are located 15 centimeter apart. Let us visualize this. We have 2 charges here. Maybe I shall draw the first charge here and the second charge here. The question says both of these are separated by a distance of 15 centimeter. So I shall write 15 centimeter between them. Okay. one of the two charges is 3 into 10 to the power of minus 8 coulomb. I'll call that point A. And point B has got minus 2 into 10 to the power of minus 8 coulomb. That's the charge. Well, when that is the situation, how do you go about solving this question? Let's find out. At what point on the line joining the two charges? So there is a line joining the two charges. Let me draw that out as well. So we have the line joining these two charges, right? This is the line joining these two charges. Is the electric potential zero? So you need to find on this line at what point or points is the electric potential zero due to both of these charges. So how do you solve that question? Very simple. Watch. Let's say that this is one point and this is another point. You need to realize that the potential becomes zero on either sides of the smaller charge. Out of 3 and 2, forget about the minus sign. Out of 3 and 2, 2 is a smaller charge. So the potential becomes zero on either sides of that charge, meaning 2 into 10 to the power of minus 8 coulombs charge. On either sides, it becomes zero, right? Let us say that the distance from the charge placed at B is x1, the place where the potential becomes zero. Maybe I'll call that place P, and then this place Q, and that is also the point where the potential due to both the charges becomes zero. So let me call that distance x2. We will be finding x1 and x2 with a lot of ease. Watch. The potential at P is simply equal to potential at P due to charge kept at A plus potential at P due to charge kept at B. So that's how I would present that. Going further, we want this to be equal to zero because the question demands us to find the distance to that particular point at which the potential becomes zero. The potential at A is 1 divided by 4 pi epsilon naught QA divided by distance, which is, let's say, from A, it is this distance to point P, which is 15 minus x, you see. X1, maybe, I'm sorry, missed that subscript. But from here to here, it's x1. From here to here, it would be 15 minus x1. So the total distance is 15 centimeter. I shall write 15 minus x1 plus potential at point P due to B would be equal to 1 divided by 4 pi epsilon naught QB divided by x1. That's how you would do that. Well, you can just transfer one of them to this side. You will have 1 divided by 4 pi epsilon naught QA divided by 15 minus x1 being equal to 1 divided by 4 pi epsilon naught QB divided by x1 with a minus sign. Well, when that is the situation, you have 1 by 4 pi epsilon naught and 1 by 4 pi epsilon naught getting cancelled. We have QA divided by 15 minus x1 equal to minus QB divided by x1. Let's substitute for QA and QB. QA is 3 into 10 to the power of 8 divided by 15 minus x1 equal to QB is minus 2. There is a minus sign already, and then there is a minus 2 into 10 to the power of minus 8 divided by x1. Minus into minus would become plus. We have 10 power minus 8 and 10 power minus 8 getting cancelled. That was a 10 power minus 8. So we have 3 divided by 15 minus x1 equal to 2 divided by x1. That's what you would have. Cross multiply. If you cross multiply, you have 3 times x1 equal to 30 minus 2x1. You would have 5x1 equal to 30, or x1 would become equal to 6 centimeter. That's x1. Similarly, you can go about solving the potential for at point Q and find the distance x2. Let's do that. Potential at point Q would simply be equal to potential at point Q due to charge kept at A plus potential at point Q due to charge kept at B. Well, you can now have 1 by 4 pi epsilon naught pulled out as a common factor because it was there in both of them. Now I'm just pulling it out as a common factor. QA divided by the distance to point Q. From A, it is 15 plus x2, you see. Where the distance from A is 15 plus x2, I shall write it as 15 plus x2. And then I have QB divided by the distance from B to point Q is x2. I shall write x2 there. Well, this has to become 0. Cross multiply and you get a 0. Please transfer it to this side. You have minus QA divided by 15 plus x2 becoming equal to QB divided by x2. Well, going further, we have QA, my dear friends, being 3 into 10 to the power of minus 8. I have, of course, there is, all right, QA is 3 into 10 to the power of minus 8 divided by 15 plus x2 equal to QB is minus 2 into 10 to the power of minus 8 divided by x2. I have minus and minus getting cancelled. Let's cross multiply. We have 3 into x2, 10 power 8 minus 8 also goes away. 3 into x2 is equal to, we have 15 into 2, that's 30 plus 2 x2. So this simply implies that you transfer this here, it simply becomes x2. X2 becomes 30 centimeter. That's the answer. We have, because 3x2 minus 2x2 is simply x2, and x2 becomes equal to 30 centimeter. That's how you solve this problem, and here is the complete view. Okay, so here is the complete view of the whole question, and if you can practice this, that will save your day in the exam in case this question comes. So let's sit and practice. Let's go to the next question. Let us look at the next question. Calculate the effective capacitance between points A and B as shown in the figure is the question. So we need to find the effective capacitance between A and B. It simply means that a battery is connected across A and B so that this system gets charged, right? How do we go about solving this? Let's find out. Let us first find the effective capacitance of these two capacitors, right? So let's find the effective capacitance of these two capacitors. Well, these two capacitors, my dear friends, are in series. Look at this. They are connected end to end. Then the effective capacitance, let's say I would like to call it C. Let's say I call it C. It's not visible. Okay, maybe here C1, right? That's C1. And maybe this bit that we have all the way from here to here, this bit, let me call that C2. This is C2, right? That's C2. And both of C1 and C2 are in parallel, so their capacitances would get added up. So we have C1, my dear friends, equal to these two, multiply these two, because it's simply 1 by C1. When they are in series, C in series is 1 by C1 plus 1 by C2 and so on till the nth capacitor, which simply means that if you have two capacitors in parallel, you can simply say first capacitor into second capacitor divided by first capacitor plus second capacitor, meaning in this case 9 into 3 divided by 9 plus 3. Let's try to do that. 9 into 3 divided by 9 plus 3, my dear friends, this is going to be 27 divided by 12, which is as good as 9 divided by 4, which is 2.25 microfarad. That is the capacitance of C1. That's capacitance C1. What is capacitance C2? A similar job now. C1, C2 divided by C1 plus C2. So 12 into 4 divided by 12 plus 4, which is simply 12 into 4 is, you can just cancel it out here. We have 12 into 4 divided by, this is 16 for 4. The answer you get is 3 microfarad. Well, do you see that the upper branch has a capacitance of 2.25 microfarad and the lower branch has a capacitance of 3 microfarad? The sum of these two would be effective capacitance of this whole branch. So if you can think about this whole branch, this maybe, well, this whole branch now, that whole branch, okay, not this one included. All right, something of this sort. When all of them are combined, these two are now in parallel. When they are in parallel, the effective capacitance would simply get added up. So maybe I'll call it C effective, right? So let me just call that C effective. C effective would simply be equal to, I mean, just of this particular branch, would be equal to C1 plus C2. C1 plus C2 is 2.25 plus 3, which is 5.25 microfarad. That is the effective capacitance of this branch. The total net capacitance, the net capacitance has to be figured out, which is 2 microfarad in series with this whole thing. The whole thing is 5.25 microfarad, and then that is also in series with 6. So the total capacitance CT I shall call, which is basically the total capacitance, it's equal to 1 by 2 microfarad plus 1 by 5.25 microfarad, 5.25 microfarad plus there is 6 microfarad, 6 microfarad, and you solve this, you are going to get the total capacitance as 1.168 microfarad, and that happens to be your final answer. That's how you solve capacitors in series and parallel. It's quite a simple question, can appear in competitive exams as well. Let's practice.